we've introduced the idea of the inverse of the exponential. We called this new function the log, and the log depends on which exponential we're working with. So if our exponential is y equals a to the x, a is some number, its inverse, we're going to call it log base a. And we have these basic properties, and that if this is the inverse, that implies that if y equals a to the x, we have x equals log base a of y. Also, if we compose these functions, it just returns the original number here. So log base a of a to the something gives me that same number back. Likewise, a raised to the log base a of something gives me that same number back. Okay. What we're going to do now is try to figure out if we can find some properties that these things hold. And the reason we're interested in this is we know that the exponential has nice properties. So for example, we know that if we take a raised to the u plus v, that's the same thing as a to the raised to the u times a raised to the v. Also, we know that rephrase this, that if I take a raised to the u and raise it to another power r, that's the same thing as a raised to the u times r. Okay? And it's going to turn out that because the exponential has these nice properties, the logarithm is going to have some similar properties that are going to arise from this. Okay? So let's see if we can tease this out. Okay? So let me put these off to the side, so keep them in mind. Okay? So I'm going to write it a slightly different way. So a to the s times a to the t is a to the s plus t. A to the s divided by a to the t is a to the s minus t. Okay, that's another property we've had. And a to the r times s is a to the s all raised to a to the r. Okay, so we're going to keep those in mind and work with them later. So let's see what happens. So let's start with two different numbers. We'll call the numbers u and v. And I'm going to assume that u can be written as a to the s, and I'm going to assume that v can be written as a to the t. So this means that u is a positive number and v is a positive number. So what does this mean? This means that u times v is a to the s times a to the t. Using this property here, I know that that is true. Okay. So let me take the log of both sides and see what happens. So I take the log base a of u times v. That's going to be the log of log base a of this number, like so. And now, because these are inverses, log base a of something is going to be the something. And now what is s? Well, notice, what do we have? We have a to the s there, and we're trying to figure out what that is. So let's just call that, so we know that's equal to u. If I want to get what s is, I can take the log base a of both sides of this, and log base a of a to the s is just s. So that says that s is equal to log base a of u. Likewise, if I have a to the t equals v, take the log base a of both sides. So now log base a of a to the t is t. So s, so let me rewrite this now. So the log base a of u times v is going to be s plus t, but s is just log base a of u, and t is log base a of v. Okay. So I've got this nice property now that, let's see, log of u times v, that's base a, is log base a of u plus log base a of v. Okay. Now let's turn this around and think about what happens when I take u divided by v. So let's change this a little bit. This becomes u divided by v is going to be a to the s, or a to the t, It's going to be a to the s minus t using this property of exponentials. We take the log of both sides. Okay, so take log base a of both sides, and we'll leave this side alone. Log base a of a to something is just the something. But what do we have? We have that log of a u divided by v is s. That's going to be log base a of u minus t, which is log base a of v. So in terms of my properties now, I've got a new property, log base a of u divided by v is log base a of u minus log base a of v. That's a mess. I'm going to come back and rewrite it afterwards. Just want to use that to keep track. Okay, so this property gives us this nice thing. This property gives us this nice thing. And now we're going to try to take a look at this and see what happens. So let's stick with that. So what do we have? So let's look at u raised to the r. It's going to be a to the s raised to the r. It's going to be a raised to the s times r. So I'm going to take the log of both sides. So what do I get? So I'm going to take the log base a of u to the r. Is log base a of a raised to the s times r. Log base a of a raised to something is just the something. And what did we say? We have that s from before. So this is going to be, we write this as r times s, but s is just log base a of u. Okay, so I've got this third thing here that we can write, that log base a of u to the r is r times log base a of u. Let me rewrite that because that's a bit of a mess. So these three properties are, I have a to the s plus t is a to the s times a to the t. A to the s divided by a to the t is a to the s minus t. A to the s all raised to the r is a to the s times r. Okay. And then that means then this property right here implies that log base a of u times v is log base a of u plus log base a of v. This property implies log base a of u divided by v is log base a of u minus log base a of v. And this property implies that the log base a of u to the r is r log base a of u. Okay, so let's see if we can look at a couple examples here and see how this is going to help us to do things. All right. This is okay. All right, so let's start here. Okay. Suppose I have that. Now, if I didn't have any of these properties, I would just take log base 5 and work from there. The problem with that is your calculator probably doesn't have a log base 5 button on it. It only has log base 10 and natural log. And the reason why your calculator only needs those two bases is because of this property right here. So let's do the natural thing. Take the log natural. So if you take the natural log of both sides, I have something raised to a power. Here's something raised to a power. I can bring that x out, that power out, get that, and now I can divide both sides by log of 5 to get that. Okay? And because of this property right here, basically, if I can do anything in natural log or log base 10, I can deal with any base, right? So basically, I just take the log of everything, and I know I'm going to be able to bring powers down and work from here. And yeah, okay. Let's do one more example. Let me complicate this just a little bit. So let's stay with the same thing. Okay, let's make this 3 times 5 to the x equals 7. Okay, so now, just looking at this, you may think, I can't just take the log and hope things will work out, because that property isn't there. But notice I can think of this as multiplying two things, so I'm gonna use this property and then use this property. So I take the natural log, 3 times 5 to the x. So this is a brute force method. Basically, I'm just take the log of everything. This is not in this form, so I can't use this property, but it is in this form. I'm multiplying two things. So I'm going to use that property. Now let's see, this is just some constant number. Let me subtract it from both sides. So I get that. And now I can use this property. I can bring that power down. That's a natural log. Getting excited. This is just some number, log of 5. This is just some number I can punch in the calculator. We divide both sides by that. So there's what I have on the right-hand side. I'm going to divide the whole thing by that number, and there's my solution. Do one last example. And again, I'm just going to try to use whatever properties I have. And the key thing here is to know is that I can just use brute force. If I have a big long expression, I can take the, and I've got exponentials somewhere, or I have this add or subtract logs. I can basically try to use these in some ways to collect pieces together. So in this next example, I'm kind of going to go backwards, and I'm going to start with a log. And I'm going to use things on the right-hand side to make them look like on the left-hand side, and then use the inverse to bring them back. Okay? So let's see. So for my example, I'm going to have log of x minus 2 minus log of x plus 2 equals 8. Okay. So I may be tempted to just raise everything to the e, and I could do that. That would work perfectly fine here, but I'm going to do it a different way. I'm going to use this property instead. So either way works fine. There's many ways to tackle this particular one, but I want to play some games with these properties today. So log of something minus log of something is the same thing as this first thing divided by that. Okay. And now I've got log of something equals something. Now I want to get rid of that, so I'm just going to take the exponential of both sides. So e to the 8. I know I can do this because these are inverses. If I compose these inverses, e to the log of something is just the something. Okay. Now let's see, I've got things, numerators and denominators spread out, so I'm going to get everything out of the denominators. And multiply both sides times the denominator here, x plus 2. I'm going to multiply this through. So I've got an x there, an x there. So let me subtract this from both sides. Okay, now I've got a constant here, so I'm going to add that to both sides. Now I can factor out an x. And I can divide both sides by that number. To get that, okay, and I put that in the calculator and work it out, and what did I get? I got a number that was something like that, a little bit bigger than, or a little bit smaller than -1. So now I got a problem here, and that if I come back and I plug this number back into this equation here, this part of the equation, -1 minus 2 is negative, so that is wrong, so there's no solution.